Welcome back to Organic Chemistry here at 8 a.m. I am your host, Dr. David Urban. Anyway, so today what we're going to do is we're going to continue on with Module 5, which is stereochemistry, and we have a group activity related to the stereochemistry. Now, remember, stereochemistry is all about fixed in space, things that have differences in space. And so for the activity, what we're going to do is we're going to assign RS, or not chiral, to a set of compounds that have 4 bonds to carbon. And we're also going to assign E and Z to a set of compounds to make sure that we have that those are also stereoisomers, and they have a specific way on naming them. Okay, where we left off yesterday was last week, we were talking about enantiomeric excess and optical activity. So let me go ahead and share my screen and put that up here. And let me put my participants over there. Okay, so we were talking about Fischer projections and how to convert your standard drawing of what we would have with wedges and stuff into that Fischer projection. And that Fischer projection actually does some really cool things for us because it makes it easier to draw, and it makes it easier to create the other enantiomer when we have more than one stereocenter. Okay, so we were able to use that by knowing that when we orient the material, only the chiral center is in the plane of the paper. Things on the y-axis go behind the paper and therefore have those wedges, and things that are horizontal go above the paper, which gives us those solid wedges. Okay, so that makes it easier to draw that Fischer projection, but we can also use that to help us assign R and S and look for the mirror image of it when we draw it as an enantiomer. Okay, so we were able to take a drawing of a compound here, orient it correctly by rotating around the center bonds, so the long axis of the long carbon chain is all along one axis, and then we saw where the different groups were. The 2 OHs are on one side, the 2 hydrogens on the other. So when we rotated it 90 degrees and presented it as the wedge structure, we got to this guy right here, which then converts to this Fischer projection. Now notice, once we get to this Fischer projection, especially when we have 2 stereocenters, it becomes easy to see whether or not we have a mirror plane or not. And in this case, we have, when we draw a line through the middle of the molecule, the top and the bottom look the same. And when we see that happen, that's our mirror symmetry. That makes this an achiral molecule. It has 2 stereocenters, but it is an achiral molecule and does not rotate light. Okay. However, if we took the other isomer of it, notice this is the you could almost call the cis isomer up here on top, where they're opposite each other. Right here on this one, they're sticking out the same side. When we do that same rotation of rotating this down, we actually end up with the OH groups on opposite sides, so that when we rotate it 90 degrees and put our long axis on the Y here, we end up with the 2 OHs on opposite sides. So when we get our Fischer projection out of that, we end up getting no available mirror plane. If we draw it here, we have H and OH. So the H and the OH don't match. So there's no mirror plane, and there's no mirror plane here because the H and the OH don't match either. So that means we have successfully converted our 2R dot, 3R butane 1,2,3 diol into a Fischer projection. And we also know that it's optically active because there's no plane of symmetry. Now, what we can also do, which is really cool with this Fischer projection, is we then find out we can put a plane there and make the other isomer of the pair of enantiomers by just drawing it there. So let's look at that interrelationship, okay? So that interrelationship, when we have a compound drawn with our wedges and such, we know that we can turn it into a Fischer projection by making sure our long axis is along the bottom here, and then assigning where our wedges and our um, dashed wedges are, so that when we get it assigned on our vertical axis here, we then have our specific locations correct. Once we have that, we can then draw our Fischer projection. Note, we can assign this as S using our hand method for this or using the book method. If we were going to use the book method, we'd have to rotate the hydrogen back 120 degrees. This methyl group comes out 120 degrees and the chlorine goes here, giving our assignment of 1, 2, 3. So that is going to be 1, 2, 3, which is counterclockwise, which is our S. Make sure that you can do that conversion, okay? Either by that or by looking at it through your hand. Actually, using the hand on this particular drawing makes it fairly easy because when you have your hand like this, your hydrogen is already sticking out at you, and then your methyl group is up, your chlorine is here, and your longer chain is here. So we have 1, 2, 3, 1, 2, 3. And if we look at it, it's counterclockwise and we can assign it S. So that's why I like the hand, because you can order your hand, orient your hand to match the picture on the page. And then when you turn it around to look down at it, you can get the R and the S correctly. Okay. And we can do the same thing on the bottom here, and we'll see that it turns into S. Okay, so that's the cool thing about our Fischer projection. We're converting it into here. Now, all we have to do is draw our mirror plane, and we draw our mirror image, and we get our enantiomer right here. So these two are enantiomers to each other because they're mirror images and non-superimposable. We know they're non-superimposable because one of the stereocenters has a chlorine on it, one of them has a bromine on it, and so there's no way they can be mixed in space. Now, the other cool thing about this is that when you have your Fischer projection right here, once you've assigned the R and the S to one set, in the mirror image, it's going to be the opposite of it. So both of these are S, noted both of these are R. Okay, so that's a great thing about this Fischer projection, is that once you know, you only have to really kind of assign one set and then you can go from there. Okay, the other thing about it is, okay, so we have two stereocenters. That means we must have diastereomers. So that means there should be another pair of enantiomers somewhere. How do we convert that? Well, using that Fischer projection, it makes it fairly easy to find the next set of diastereomers, because all we have to do is take one stereocenter, and I'm going to take this stereocenter here, and all we do is swap two of the groups right here, changing it from the S to the other one, or changing it from whatever it is to the opposite of it. And in that case, we've moved it here, and all we've done is switched one stereocenter, okay? You don't want to switch two stereocenters, that mixes things up. You want to switch one stereocenter, and that becomes the first isomer of your other pair of enantiomers. Now notice we've changed this, so this is now R, but the S is still an S on this side, okay? So our first pair of enantiomers is SSRR. Our next pair of enantiomers is going to be RS and SR, okay? Now, because you have two different sets of because you have two different assignments on those, that means this set right here cannot be enantiomers with the other set, but they have all the same connections, so they are diastereomers of them. Okay. Now, we're going to use that same trick to draw the other isomer by taking our mirror plane, putting it down the middle, right here. Our mirror plane, putting it down the middle. And notice the hydrogen goes to hydrogen, the chlorine, and the methyl here. And then our hydrogen, hydrogen, bromine, bromine, and methyl group here. So we've just done that mirror image working from the center out. Now, again, we don't have to reassign these things because we know this one was R. This one was R, which means when we make the mirror image of it, it automatically becomes S. And this one was S. And when we make the mirror image of it, it automatically becomes R. Okay, so now we have two sets of enantiomers, and we have a total of 4 compounds that are diastereomers of each other. Okay, does Any questions on that? Okay. So this is the real good thing about the Fischer projection. It makes it very easy to go from one to the other, to go to the enantiomers and to the diastereomers. Enantiomers, you do mirror image. Diastereomers, you switch one stereocenter. So that's how you can do that. Notice that if we went from this one, we would switch this R to an S, switching one stereocenter, and we would get that diastereomer. Okay. And notice on this one right here, we're switching, let me draw it in a different color here, this blue one, this R, into an S here. So going from diastereomers, we're only switching one stereocenter in each of those sets. Go ahead and practice that and see if you can prove it to yourself. Okay. Questions on the interrelationships and the usefulness of the Fischer projection? You can tell I'm a morning person, right? Okay. Okay. So that's great and all, but what if you have more than two stereocenters? Well, like we said before, it's going to be 2 to the power of how many times you have stereocenters. So in the case of 3 stereocenters, you have to have 8 possible stereoisomers. But what that means is you're going to have a pair of enantiomers with those, right, that are going to be superimposable mirror image, non-superimposable mirror images. And so what you're going to end up is having 4 sets of enantiomers. And from that, you're also going to end up with that set of 8 diastereomers. Okay, so let's look at that. And luckily, these are assigned for us because it'd be long and hard to do them all. But notice this is 1R. So this is R1, this is R2, and this is R3, going around a ring. That's not priority, that's just our ring number, because the chlorine, oh, actually it's named for the alcohol, so I'm numbering it incorrectly, ha ha ha. So because it's named for the alcohol, we start at the 1, this is 2, and this is 3, because that's the lowest number. So that means our OH group is on that number 1 carbon on all of these isomers, okay? So in this first one, we have the number 1 is assigned as R, the number 2 is assigned as R, and the number 3 is assigned to S, okay? So its enantiomer is going to be the 1S, 2S, 3R. Notice how each of those stereocenters has gone to the other one to give us that set of enantiomers. Now, by changing one stereocenter, in fact, in this one, we're going to be changing the 2. We're changing the 2 from R here to S here, and we end up with our next set of enantiomers. And we have RSS, which means we go to SRR. Okay. And then this becomes our next set of diastereomers by changing one thing. The only one we changed was this 3 from here. We changed it from S to R. And then, of course, these all switch over to SSS because these were all RRR. Okay. And then our last set of enantiomers is, let's see, we swapped, let's see, RRS. We swapped this one right here with this one right here, and we get SRS and RSR. So we have 4 sets of enantiomers. We have 8 possible stereoisomers because we had 3 stereocenters. But going from one enantiomer, set of enantiomers to the next set of enantiomers, we switch one chiral center only, and then we find its mirror image. Questions on that? And then, of course, if we had 4 stereocenters, we'd have 16 possible stereoisomers. But don't worry, I'm not going to do that to you today. All right. So the other great thing about the Fischer projection is it makes it easy to see those mirror planes, okay? And I might have said this before, but when you have a mirror plane in a system, it makes the material achiral or non-chiral, okay? Which means that if you found a mirror plane in one of your sets of diastereomers, in one of your diastereomers, it will not have optical activity, okay? So let's look at that with this right here. I believe this is tartaric acid. Okay, okay. So if we look at this set of enantiomers here, we have RR and SS. So we have a pair of enantiomers here. And, the only thing, these are all lining up here. And if we try to draw a plane here, we have H and OH. So there is not a mirror plane in this set of diastereomers. And when we look at the properties, we actually find out because they're enantiomers, they have the same melting point, they have the same boiling point, but they have equal and opposite optical rotation. Okay, so this particular isomer has a plus 12. This particular isomer, because it's the enantiomer, has minus 12. Okay, so we're going to do that same thing with the Fischer projection, going from the one set of enantiomers to the second set by flipping one stereocenter. Okay, in this case, we're going to flip the lower stereocenter. And so to do that, all we do is move the OH over here and the H over there, and we get the S orientation on here. So now we have our RS conformation here. So first of all, if we draw a mirror plane, we have a mirror plane. We have OH and OH here. We have the carboxylic acid, hydrogen, hydrogen. All right, so at least that compound has a mirror image. Let's draw its enantiomer to make sure. So we go OH to OH, carboxylic acid to carboxylic acid, and then hydrogen to hydrogen. And when we do this, we see that our stereocenter inverts on both of these, but we still have a mirror plane here. Okay, what does that mean? Okay, because of that symmetry element, because of that mirror plane, we lose optical activity. Okay, we have two chiral centers in a compound, but it has zero optical activity. We call this a meso compound, M-E-S-O, meso compound. So technically, we can draw the diastereomer as a set of enantiomers, but they're the same compound. You can actually, if you just take this, rotate it 180 degrees, it will overlay this completely. Okay, so that means we only have 3 isomers in this set here, okay, in this set of diastereomers, because there was the mirror plane. When we have that mirror plane, it's called a meso compound. Okay. And it's really easy to see in these Fischer projections. Okay, questions on losing optical activity even though we have 2 chiral centers. Remember, it's all about that mirror plane. If it has a mirror plane, then as the light interacts it can look at it either way and it's going to be the same, and therefore it doesn't rotate light. Now notice that there's 0 optical activity and it has a different melting point. Remember, diastereomers can have different physical properties. Enantiomers have the same physical properties except for optical activity. Okay, so that brings us into this interconversion again. Okay, so in this one, this is a great exercise to do on your own, to look for the diastereomers and look for the enantiomers. We're going to start with our compound here, rotate it so our longest carbon chain is facing down, convert that into our wedge drawing, and then convert that into our Fischer projection. And in this case, we have an S here and an S here. So when we draw our mirror image for its enantiomer, we should get an R and an R. Okay. So now we have that pair of enantiomers here at the top. Okay, so how do we get to the diastereomer again? We flip one stereocenter, and in this case, we're going to take this S and convert it to an R. That's how we get to our diastereomer. When we do that, we see immediately in our Fischer projection, we have a mirror plane. When we see that, we know we have a meso compound. So what that means is we now have a pair of enantiomers and a set of 3 diastereomers, because these are the same. Question? Okay. So in the previous one, we ended up with 4 compounds that were diastereomers, 2 sets of enantiomers. In this one, we found a mirror plane. And that mirror plane is very easy to find using that Fischer projection. And therefore, we only have 3 isomers available to us because one is a meso compound. All right, let's move to the other type of stereoisomer we have, and that's not with 4 things bonded to carbon, but with something fixed in space, specifically 4 different things bonded to an alkene. Okay, so we have diastereomers in these alkenes. We do not have RNS, but we do have diastereomers. The key here to have a diastereomer is that you need to have the same 2 elements attached to the same side of the double bond. Okay, here's what I mean. On this side here, we have a carbon, and it has a fluorine and an iodine attached to it. This carbon has a fluorine and an iodine attached to it, but they're flipped in space. Now, remember, there's no rotation on that double bond, so it is fixed in space. Therefore, they are identically with the attachments, but they are different in space. Therefore, they're a stereoisomer. Okay. Notice that if we change it such that we have a different element on that same side of the double bond, that is not a diastereomer. That is a structural isomer. Okay. So that is a structural isomer because we've changed the connections. We have a different element on that same side of the alkene. Therefore, it's a structural isomer and not a diastereomer. So see how this right here is a diastereomer because it's a pair of things that have the same connection except they're different in space. Okay. And how these are structural isomers because we've changed what things are connected. Here we went from a bromine to a fluorine on this side, and we went from a fluorine to a bromine on this side. Therefore, we've changed that connection. Remember when we do E and Z, we always cut it down the middle? We look for what's attached to half of it, what's attached to half of it. If it changes, it's a structural isomer. If they're the same but just different in space, they're a diastereomer. Okay. Questions on that? Okay. So that double bond gives us a fixed in space set. Okay. But there's also something else that can happen when we move to cyclic alkanes. Okay. When we go to cyclic alkanes, we have to start looking for mirror planes and whether or not we can see if they are the same or different. Okay. So let's take this cyclopropane here. So we have cyclopropane, and these are just drawn straight up and down because they're really technically, canted out and they're technically eclipsed. But if we just had the one X, like just this was a hydrogen here, we only have one isomer because no matter how you flip it around, it's exactly the same compound. So if we put a second one on here, we have a couple different ways we can do it. The first way we can do it is what we call the 1-1. Notice they're both on the same carbon here. Okay, so if they're both on the same carbon, then again, any way you spin it, no matter which carbon they're on, it's going to be the same compound. So that's one compound by itself. Okay. Now we can also have it where we have them on the 1 carbon and the 2 carbon. And if they're on the same side of the ring, we would call that cis 1,2. Notice we have them on the same side of the ring and they're on the 1 and 2 carbons here. We only have one isomer of that because you can flip it and turn it and it will overlap with itself. So we only have one isomer for that. Okay. Now, if what we do is we take it from the cis configuration to the trans configuration, see how those 2 X's are on opposite sides of that ring? So that's our trans configuration. However, because they are unique in the sense that if you draw its mirror image, it's not superimposable, you actually end up with an enantiomer here. If we drew our mirror plane here and we put this up and this down, if you flipped it over to try to overlay it, the second X would show up here and the first X would show up there. And so they would not be able to overlap. Therefore, they have a chiral center. And so we have a pair of enantiomers. So that means we have 4 isomers possible with adding 2 things to cyclopropane. Okay. Okay. And there's no mirror plane. Let's see. Is there no mirror plane? Yeah. So there's a mirror plane here, but it's still one compound. There are no other compounds available to us. Okay, so what if we extend that one more carbon and look at the cyclobutane? Okay, once we get to cyclobutane, we end up with only, again, one isomer if we have one attachment, because we can just rotate it around until it overlaps. However, if we have two attachments, we end up with 6 isomers. Okay, just like we did before, we're going to start with both of them on the same carbon here, both of them on the same carbon here. And what we'll notice here is immediately that we have a mirror plane in that one, because the two X's can line up with the two hydrogens on the other side, and we have a mirror plane. Now we're just looking for it. So that compound is not chiral, but it is a compound. It's a non-optically active compound. Now, if we go from the 1,1 to the 2,1,2 cis, where we have them next to each other, we also have a mirror plane, which means we don't have a pair of enantiomers. We have just one compound available to us. And then if we go to the 1,2 trans, we can draw a non-superimposable mirror image, because if we try to rotate this 180 degrees, our X would show up here and here, and therefore they are non-superimposable. Okay, now let's move from 1,2 to 1,3. Once we get to 1,3 cis, 1,3 trans, we actually end up seeing planes of symmetry in here, meaning each of those only has one isomer, because we have a plane of symmetry. Therefore, we cannot have a mirror image that is non-superimposable. So that means we have 1 for this, 2 for that, 3, 4, 5, 6, and only 6. This one right here is actually the same as its mirror image because of that plane of symmetry, and therefore we have a total of 6 isomers possible. All right, questions on cyclohexanes? I'm sorry, cyclobutane. All right, so then there's some crazy compounds that are chiral, but they don't have a chiral atom. Okay, now they're chiral because they have a 3-dimensional fixed in space. Okay, and in this case, we have a group of compounds called allenes, which is where we have 2 double bonds, 2 double bonds across 3 carbons. Okay, now note that this is sp2 hybridized, this is sp hybridized, and this is sp2 hybridized. So why is it fixed in space? Well, first, it's a double bond, so we know it has to be fixed in space. But why are these, notice these have lines here, so they're in the plane of the paper, and these have dashed and solid wedges, so they're coming in and out of the paper. So why do we do that? Well, let's think about this. With this carbon here, we have 1 p orbital available to make a pi orbital, a pi bond. And so we're going to draw it like this in that orientation. So our pi bond is in that configuration right here. Okay. Now, we can't use that same p orbital to bond with the other carbon. So luckily, we have our center one is sp. So it has another one available to it. So we're going to put that 90 degrees from the other p orbital. And we're going to line that up with that p orbital available over here, making our pi bond here. Okay, so 1 pi bond is in the horizontal, 1 pi bond is vertical, which means the bonds that are on this sp2 carbon are in that plane. Those 2 bromines are in that plane. And the 2 hydrogens are in this plane, and therefore go in and out of the board. So in this particular case, we have 2 bromines on one side, 2 hydrogens on the other, and it actually has a, it's the same compound, because all you have to do is rotate it around and it becomes the same compound. However, if you put 1 bromine on each side, you now end up with them uniquely fixed in space. The 2 bromines are 90 degrees from each other across those 3 carbons, and therefore we can go to a non-superimposable mirror image, and we have a pair of enantiomers. But the key here is that we have chirality, we have a fixed in space point, because one of the p orbitals is in 90 degrees from the other p orbital, and that 3-carbon center makes that attachment, that fixed in space attachment. So it's technically a chiral compound without a chiral atom. Okay, so I did not need my watch, sorry. Okay, so in review, structural isomers are different compounds with the same molecular formula, and they can have different functional groups. Okay, constitutional isomers have a different order of attachment. Okay, so think about that as, different compounds, same molecular weight, or they're just like you move a methyl group down. Even though it has all the same functional groups, you just move the methyl group down the chain. Okay, so that's constitutional isomers. Okay, stereoisomers are different compounds that have the exact same connectivity, except their arrangement in space, and stereo is space. Geometric isomers are stereoisomers that differ in which side of the rigid part of the molecule the different groups are on. So we can have geometric isomers that are different in space, so they're stereoisomers. The chiral object is a non-superimposable mirror image. An achiral object is something that does have a superimposable mirror image. Okay. Enantiomers always come in pairs, and they are the mirror images of each other. And the only way we can tell them apart is that one rotates polarized light one direction and one rotates polarized light in the equal and opposite way. The next thing we have is diastereomers. So we have more than one stereocenter. We have a pair of enantiomers. We might have a pair of enantiomers giving us a set of diastereomers. And we have those number of pairs depends on how many stereocenters we have. 2 stereocenters, 2 pairs. 3 stereocenters, 8 pairs. 4 stereocenters, 16 total compounds. So let's see, did I say that right? 2 stereocenters, 2 pairs of enantiomers. 3 stereocenters, 4 pair of enantiomers. 4 stereocenters, 8 pairs of enantiomers. Sorry, said that wrong. Now, if any of those diastereomers has a mirror plane in it, it's called a meso compound, and because they will be able to overlap with themselves, and that becomes achiral or non-chiral. Okay, and this is a nice little visualization of that. Questions on stereochemistry before we convert over to our group activity? I don't have anybody muted. Okay. All right, I'm gonna go ahead and stop sharing and pull up the group activity and then give you some instructions. Where's the group activity? Oh, that's right, it's over here. I thought I downloaded it again, and I keep not downloading it. Okay, group activity, activity 2, chirality. Don't give you the key. Yeah, all right, there we go. So I'm going to share my screen again and give you some instructions. Okay, so here we go. We have our group activity. I sent it out to you yesterday. You can use a digital or electronic copy. What you want to do is you want to assign R and S to the first page. Now, remember, the first rule of R and S is it has to have 4 different things. So count to see if you have 4 different things, and then if it doesn't, just leave it blank. It is not a chiral compound. If it does have 4 different things, use R and S. Now, note the first 2 have the hydrogen facing away to make it easy to assign R and S, but then it gets harder and harder as you go. Now, trick is those 2 longer compounds on the right side there, there's only 1 chiral carbon in each of those compounds. So you only need to assign the 1 chiral carbon in each of those. Okay, so we're gonna break out into breakout rooms, and you're gonna do this as a group. Remember the 3 rules of prioritization. Atomic number, if that gives you priority, you're done. You don't have to worry about anything. And can you see my screen? No, it's screen sharing is paused. Let's try to share it again. There we go. Can we see my screen again? All right. So the look for the first two here are really, I mean, the first three right there have the hydrogen facing back, so it's easy to see. The two on the right there are the ones that only have one chiral center. So the two long ones. So don't try to find more than one chiral center there. All right. And so then you would assign it in each of these boxes. If you didn't print this out and you want to do it on notebook paper, just arrange them in the same order and assign R and S, put the little boxes in that same kind of configuration, 4, 4, 3, and I should be able to figure it out on SpeedGrader. Okay. The second page, don't forget the second page, is assigning E and Z. Now remember, when you're assigning E and Z, you go by atomic number. If that satisfies your prioritization, you're done. If it doesn't, you have to go to rule 2, which is go out until there is a difference. And there's at least one or two you have to assign rule 3. Rule 3 is that if you have multiple bonds to different atoms, you have to count them. For example, if you have a double bond to a carbon, you count that, a double bond to an oxygen, you count that as 2 oxygens plus whatever else it's bonded to. So that's rule 3 in prioritization. And again, E and Z, you just prioritize one half, prioritize the other half, and assign E and Z. Remembering that E is opposite each other and Z is together, or Z, Zame, Zi. Okay? So questions on what to do in the group activity. Okay. Once you complete this, I'm going to give you the rest of class period to do that, and then I'm going to bow out right at whenever our class ends at 9:20. And then all you have to do is complete it and upload it to Canvas by midnight tonight. Okay? Okay, you got 45 of us here, so that will break us out into about 9 rooms of 5 each. And so that would give us a nice group size so that everybody gets a chance to talk. Remember, introduce yourself, be polite, work through the rules, and try to help each other figure things out, okay? And then try the different assignment techniques. If you're going to use the paper stuff, use the rotating on paper. If you're going to use your hand, use that to do your assignments of R and S. Okay. All right, I'm going to stop sharing. And I'm going to stop recording because I'm going to break you out.